in the first of the experiment that we are going to discuss, we will be discussing the op-amp in negative feedback. Op-amp in negative feedback to design amplifiers as well as instrumentation amplifiers. Let us consider first the op-amp itself. It's nothing but a differential input stage with V1 at one and V2 at the other end of the input, such that output is A times V1 minus V2. A is called the differential mode gain, and it is biased by dual supplies plus VSS and minus VSS, so that the output quiescent voltage is designed to be zero, okay, or it has zero offset when the input is zero. Now with this kind of op-amp, as V0 is kept finite, V0 by A, which is nothing but the difference in voltage at the input, this tends to zero, or V1 becomes essentially close to V2, okay, for any finite V0 as A tends to A. This could be a current amplifier. Again, the same current gain as it tends to zero, I1 tends to I2, or the input differential current goes to zero. So essentially, finite output really means that it is within the saturation states plus VSS on one side and minus VSS on the other side. As long as the output is within this range, you can assume that V1 is close to equal to V2. And therefore, we come to an important characteristic of the output of the op-amp. Output of the op-amp goes to saturation at certain point with a certain gain for the input. So if you plot Vs versus V0 for the amplifier with feedback, now this factor becomes 1 over beta. If beta is 1, output by input becomes. So we had just seen the unity gain amplifier. Now extension to non-unity gain, that is higher gain amplifier, non-inverting, is very simple. That instead of the full feedback, we are now giving partial feedback. Put an attenuator in the loop. Okay, and that attenuation is R1 by R1 plus R2. This let us call it as beta. That means if V0 is the output voltage, beta V0 is feedback. And now this is again the same as Vs, and therefore Vs becomes equal to beta V0, or V0 over Vs is 1 over beta ideally, and therefore it becomes 1 plus R2 over R1, which is going to give you any gain you want. Suppose you want to design a gain of 2, R2 is made equal to R1. If you want to design a gain of 10, R2 by R1 is made 9. So that the overall gain becomes 1 plus R2 over R1, and therefore you can design any buffer stage here with gain, because it's still not taking any current, and you can connect any load to this. That is being given by the output stage, okay, of the operational amplifier. So we had seen the frequency response of the amplifiers like unity gain, non-inverting amplifier and inverting amplifier will be determined by the gain bandwidth product of the op-amp, which is nothing but the DC gain into the first corner frequency. The op-amp characteristic having A0 as the DC gain and the first corner frequency where the gain falls off with respect to frequency at 20 decibels per decade, and then further it falls off at 40 decibels per decade, is due to the second pole at this axis. So in this experiment, we are obtaining the frequency response of the feedback amplifier with both gain bandwidth product and the second pole taken into account. It becomes a second order system like this, and GB is replaced by GB divided by S into 1 plus S by omega D2 in this, and you get transformed to a second order. And in the second order equation, this is called the natural frequency of the system. The coefficient of this, omega naught square. Omega naught is the natural frequency of the system, and this is going to be written as omega naught q into q. Q is called the quality factor, or it is equal to 1 over 2 zeta, where zeta is called the damping factor, which is familiar to control system engineering, okay? And communication people call 1 over 2 zeta as quality factor Q. So this characterizes any second order system, and what happens with this is that there is going to be a peaking due to the fact that Q is going to be high. Q in this particular case you can evaluate by equating omega naught to square root of GB into omega D2, and Q as, okay, omega naught into Q is the gain-bandwidth product, therefore it is going to be GB, okay, divided by square root of omega D2 into GB. So it will be equal to, that is GB is equal to omega naught into Q, okay, omega naught is equal to GB into omega D2. So this will become equal to GB. So I think now that we know that, therefore Q of this system can make it very sort of transient, noise dependent, that when sort of step input is given, it will start ringing, and the ringing frequency will be close to the natural frequency of the system, and Q is going to tell us how many such peaking will occur in the ring. Right? If Q is 10, there will be 10 such peakings, okay, in the ringing that follows a step input. And that is one way of quickly determining whether the system is stable or not. We do not want this ringing to continue whenever there is a sudden change in input. That will force us from waiting for a long time, okay, for the system to come to steady state. And if the system is a first order system, then it will go on with exponential rate, and that again takes infinite amount of time for the system to come to steady state. We want an optimum result. So Q is normally made equal to 1, so that in the ringing there is just one peak, so that it quickly goes to the sort of steady state and settles there. And therefore this is a design measure. So we try to locate the second pole in such a manner that the transient response of the system becomes good. This therefore will facilitate, okay, a measurement of omega D2 and the gain bandwidth product of the op-amp. Further, we have the time response to be understood. In time response, if you give a square wave for a unity gain amplifier, a square wave of the same amplitude is supposed to appear at the output. However, it gives us a sort of rate of rise which is not abrupt but controlled by the maximum rate at which output of the op-amp can rise, and that is called slew rate. Slew rate is nothing but delta V0 by delta T of the maximum that the op-amp is capable of rising. And therefore, if you measure the slope of the output waveform, we can directly measure the slew rate of the op-amp.